Hello class. Today we're going to be talking about determinants. A determinant is a scalar quantity that represents a square matrix. So scalar just means it is a regular number as opposed to like a matrix or a vector quantity. It is a number that represents a square matrix. Today we're going to talk about how to find determinants for 2 by 2 and 3 by 3 matrices and beyond. And we are also going to be learning a method to solve systems using determinants. Determinants are indicated by the capital letter D. We can also see that just vertical brackets are used around the elements of the matrix versus the typical brackets. If you just see the vertical lines, that means find the determinant. And the way you find the determinant of a 2 by 2 matrix is you take the product of the diagonal, we're going to consider that the main diagonal, and subtract it from the product of the subsidiary diagonal. Right there. And the result from that difference is the determinant. So we're going to get some practice finding determinants of 2 by 2s. So let's evaluate the determinant of this matrix. First thing we're going to do is the product of the main diagonal. We get 2, and then we're going to subtract that from the product of the subsidiary diagonal there. That is 12. So we get that the determinant equals negative 10. Now, do note that these vertical lines around a number indicates absolute value. If they put these vertical lines around a matrix, it indicates a determinant. Determinants can be positive or negative. So in this setting with these quantities, these matrix quantities, this is determinant, and determinants can be positive or negative. So you have to think of the setting of these vertical brackets when you use them. Cramer's rule allows you to easily solve systems, and it uses determinants. The first thing you're going to do is calculate what is called the coefficient matrix. The coefficient matrix is the matrix generated by plucking off the coefficients of x and putting them as the first column in your matrix, and then plucking off the coefficients of y and putting those as the second column in your matrix. So capital D indicates the coefficient matrix of this system of equations. As always, we do have to line up x's with x's, y's with y's, the equal signs, and then the constant terms. Now we do need to calculate 2 other determinants. One is called dx, and it helps you to find what x equals. What you do to find dx is you replace the x coefficients with the constant terms s and t in the determinant matrix D. So we're replacing the x coefficients with s and t, the constant terms, and we keep the y coefficients the same right here, and then we'll find the determinant of that. We calculate then dy. dy is the determinant that helps us find the variable y. We keep the x coefficients the same, so they stay AC, but we're going to replace the y coefficients with the constant terms. And that determinant will help us to find the variable y. This only works if d does not equal 0. If it does, that means you cannot use Cramer's rule. If d equals 0, that means one of 2 things. There are no solutions, and it's an inconsistent system, or there are infinite solutions, and it is a consistent system, but there are infinite solutions. So Cramer's rule doesn't tell you which one of these it is, but it does tell you what the answer is if there is one unique solution. This is how you find x right here. And this is how you find y. You do dx over d, dy over d for x and y. Let's give it a shot. Use Kramer's rule if applicable. What they mean by if applicable is as long as d does not equal 0, you can use Kramer's rule to solve the system. So let's calculate the coefficient matrix D. We do that by finding the determinant of the matrix that is built by taking off the coefficients of x and then the coefficients of y. So let's calculate that. We get 12 minus negative 30, so that means D is 42. dx is generated by replacing the x coefficients with our constant terms, with our 24, 12, and then just filling in the rest of the matrix. So that is dx. 24 times 4 is going to be 76 minus negative 72. So that's going to be 148 for dx. This one's 96. There we go. So let's make that edit. And then we can do dy. We find dy by keeping the x coefficients the same and replacing the y coefficients with the 24, 12. So finding that determinant, I get 36 minus 120. That is going to be negative 84 for dy. We learned using Kramer rule that x is dx over d. So that's 168 over 42. X is going to be 4. Y is dy over d. And dy over d is negative 84 over 42. So y is negative 2. Therefore, our answer written as an ordered pair is 4, negative 2. And we can plug that into our system to make sure it works. Like real quickly, 4 right here, we get 12, negative 2. We get positive 12, so 12 plus 12 gives us that 24. So that gives us a level of confidence in our answer. Let's try it again. Let's calculate D. D is our coefficient matrix, the coefficients of x lined up vertically, coefficients of y. So when I do this, I get 8 minus negative 15. D is 23. To calculate dx, I'm going to replace my x coefficients with my constant terms with this 10 and negative 1 right here. And then the y coefficients stay the same. So I get 40 minus 3, dx is 37. So I can just go ahead and calculate x. It's 37 over 23 because it's dx over d. How fantastic is it that I didn't have to deal with those fractions at all in the process of solving? It's just there. Now dy, I keep the x coefficients the same, and I'm going to replace the y coefficients with the constant terms, the 10 and the negative 1. So what I get is negative 2 minus 50, I get negative 52. So y is dy over d. So that's my solution. It's up to me if I want to go ahead and write it as an ordered pair. Also, I don't really want to check this with these numbers, but in a test situation, I would definitely do that if time. But for now, I'll just feel confident. So if we wanted to use Kramer's rule on a higher dimension system, such as a 3 by 3 or greater system, I would need to know how to find the determinant of a matrix that is larger than a 2 by 2 matrix. Finding the determinant of a 3 by 3 matrix is much more involved than a 2 by 2. There is just a lot more going on. I'm going to give you a second to write down all these letters, essentially, which represent the elements of the matrix. But I'm going to make sense of all of it for you so you don't have to feel like, gosh, I have to memorize this alphabet soup of a formula, because I don't know how to find the determinant. This is not how I think of it. I think of it a little more logically. So I'm going to show you where all of this comes from. So to find the determinant of a 3 by 3 or greater, really, you can use what's called the cofactor definition. The cofactors are all of these determinants of these, what I call mini matrices. So this is a cofactor, this is a cofactor, and this is a cofactor. But let me show you how you calculate the cofactors, or how you even find them. What you're going to do is pick a row or a column to follow. The convention is following just the top row. So if we look at the top row, the first element is A. So I'm going to go ahead and write A down. Then what I do is I cross out the row in the column that A is in. I cross out the row and column that A is in, and what I get is a mini matrix right here. So the mini matrix is right there, that is generated by crossing out the row and column that A is in. So what you're going to do is take A and multiply it by the determinant of this mini matrix. And again, to find what the mini matrix is, you cross out the row and column of the element you are considering, and you get the mini matrix. So that's for A. I'm going to erase just to give myself a little room for clarity here. If I'm going across the row, I'm at B. Here's the B. And I'm going to cross out the row and the column that B is in. I'm left with a mini matrix. This mini matrix is DGFI. DGFI. So that is the matrix that gets multiplied by B. I'm sure you have noticed by now that it's minus B. With determinants, determinants have a plus, minus, plus pattern. We looked with a 2 by 2 matrix. It was AD minus BC. This one is A times the cofactor for A minus plus. If we had a 4 by 4, it'd be another minus. So the determinant has that plus, minus, plus pattern throughout the matrix when considering determinants. So that is why the middle term is a minus there, minus B. All right, let's keep moving across our row. Next, we have C. C is the last element in that row. If I cross out the row in the column that C is in, I get the mini matrix created by DEGH, which is what remains when I cross out the row and column that C is in. And so this is how I calculate the determinant of a 3 by 3 or larger matrix. I calculate the determinant of all these smaller matrices, and then you have A times the first matrix minus B times the second plus C times the third, and that gives you your determinant. Let's try it. So now I know they're asking me to find a determinant. The reason being is I have these vertical brackets, which don't say, oh, hey, here's this matrix. It says calculate the determinant of this matrix. So I'm going to use the cofactor definition to do this. I will be teaching you another way, but for now this is all we've got, so let's practice it. So let's go across the first row. Across the first row, my first element is a 1. And then what we're going to do is consider crossing out the row and the column that 1 is in. If I do that, I'm left with the mini matrix 8, -4, 2, 7. Okay. That is my first cofactor. Then I'm going to work my way across that row. I'm going to write -2 because of the plus minus plus pattern. So plus minus 2. And then I'm going to cross out the row and the column that 2 is in. And I'm left with the mini matrix 3, -1, -4, 7. Okay, so that's the cofactor for the 2. And then lastly, I'm going to work my way again across the row. Last I have plus -5. And then I'm going to cross out the row and column that the -5 is in, and I get 3, 8, -1, 2. All right, so here are my elements and then my cofactors. What I'm going to do next is calculate the determinants. This one is 56 minus -8. So what we get is 64 times 1. Next, I'm going to calculate this mini matrix coefficient or determinant 21 minus 4 times -2, -2 times 17. Just going across, it's -5 times 6 plus 8, so that's going to be -70 there, doing the 5 times the 14. So 64 minus 34 minus 70, 38 minus 70, we get -40. So it makes, in my mind, more sense to think of it as just crossing off the row and column that the element is in and remembering the plus minus plus pattern. So while some people like the initial definition with all the A, B, C, D, E, F, G's in it, I don't like that myself. So I just like to consider the generation of the mini matrices given you're crossing out the row and column that the element you are considering is in. So that's the cofactor way. You also will get the choice for a 3 by 3 to use what's called the diagonal rule. The diagonal rule, in my mind, is more fun. It's just easy to kind of, like just do it, just bang it out. So I like it for that reason. It's straightforward. You can do it with less steps, but it's up to you what you want to do. It only works for matrices that are 3 by 3 or less, so you can't use it for 4 by 4, unfortunately, whereas the cofactor method works for any square matrix. All right, so let's show you how to do it. The first step is I'm going to recopy the first 2 columns. Here's the first column recopied. Here's the next column recopied. This is called the diagonal rule because it uses the diagonal of the matrix. The diagonals, plural. So I'm going to start with the very first element and draw the diagonal for that element. So this is considered the main direction. It's the positive direction. So I'm going to multiply. That is 6. Then I'm going to keep going to the next diagonal. These are being added, so this is a 0. The product of the green diagonal is 0. You add a 0. Then you keep going. This diagonal's product also gets added. This is -5. And if I keep going, I kind of run out. I've already used everything in the first row, so now I'm done. If you're for 3 by 3, you'll have 3 diagonals going in the main direction, so this is a 1. All right, let's go against the grain. Let's go in the opposite direction. So I'm going to start bottom left-hand corner. So this is -3. Keep going across my row. That diagonal is a 0. Love those zeros. This diagonal, going against the grain again, is a +5. So this is 2. So the top Diagonals sum is 1. The diagonals going against the grain is 2. These get subtracted. So you're just going to subtract, and the determinant is -1. So you could write det A is -1. You could also do determinant of A using those vertical brackets. Either way, main diagonal minus going against the grain, the subsidiary diagonals, and you get -1. I think it's kind of fun. But you can use whatever method you want for calculating determinants. Now, we already did diagonal of this matrix, or determinant of this matrix using the cofactor method. Let's try the diagonal rule. Let's first recopy the first column and recopy the second column. We do in the positive direction. Start with upper left, go down. The first one is 56 plus. Second one is 8 plus. Last one, -30. So I get 64 minus 30, that's going to be 34. Let's go on the opposite direction. So going against the grain. So my first one, this product is going to be 40. This is going to be -8, so I have 32 so far. 6 times 7 is 42. So now if I sum these up, I get 82 minus 8, that's going to be 74. And again, it's the main diagonals minus the subsidiary diagonals, it's -40. And I think if we remember from the cofactor method, we got -40 there. Same. You're essentially doing the same math. You're just organizing it very differently. But I like it. It's kind of fun. So it's up to you. It doesn't really have a bearing at all on, it's just your choice. Here is your homework assignment. I hope you all have a great day.